Here in this video, we are going to go through quantitative examples with rolling without slipping and rotational kinetic energy. This is part two of our videos. The first part had to do with a conceptual question and a conceptual understanding. Now we're moving into the quantitative piece. So here we are in part two, our quantitative understanding. I want to start with an example where there isn't any rolling to remind us how energy conservation works, and then we'll throw in an example where there is rolling without slipping. The concept doesn't get that much more difficult, but the algebra does. And so let's go through these. First, with this example, we have a box that starts from rest and it slides down a frictionless ramp of height h, and we want to determine the speed of the box at the bottom of the ramp in terms of h and the fundamental constants. And so let's look at our picture over here. We have a box at rest initially, it slides down, and now in the final scenario, it is moving, but it's at our reference height, y equals 0. So we know the height, but we don't know the length of the ramp or the angle of incline theta. So the only option we have to analyze this is energy conservation, which means let's bring out an LOL diagram. The first step in an LOL diagram, I'll move over here so you can read everything. The first step in an LOL diagram is to identify your system. In this case, the system consists of the box and the earth, and we can choose to include the ramp, but the lack of friction means we don't need to. And now let's go one by one and look at where energy could be stored. In the initial snapshot up here, it's not moving, so there's no kinetic energy. It is at a height h, so there is gravitational potential energy, and there's no spring involved. In the final scenario, it is moving, so at least some of our blocks will be kinetic energy. It's at the reference height y equals 0, so there's no gravitational potential energy, there's no spring, and because of the lack of friction, no energy was transferred into the thermal energy account. Now looking at this, I should have the same number of blocks in each, so I say, oops, I missed a few final kinetic energy blocks, I'll add them in now. And now we can use this conceptual understanding to build a quantitative relationship that we can use to find the speed of the box. So we write this as an equation. Generally, the initial energy plus any working that's done to transfer energy into or out of the system will equal our final energy. Here, our initial energy is just gravitational potential energy, the working that's done is 0, and the final energy is stored as kinetic energy. Remembering our equations for these, gravitational potential energy is mgh, and kinetic energy is 1/2 mv squared. We look at this equation, and on both sides of the equal sign, we see that there is mass. All of these terms have an m in it, and so we can divide everything by m to end up with 2gh equals speed squared. Take the square root of both sides, and we have the speed of the box at the bottom of ramp is square root 2gh. Hopefully this reminder gives you a little bit of an idea, or at least a refresher on how energy conservation works. And now let's move into applying these same principles to an object that is rolling down a ramp without slipping. Example 3. We have a solid cylinder of rotational inertia 1/2 mr squared, m being the mass and r being the radius of the cylinder. And it starts from rest and it slides down it doesn't slide down a frictionless ramp. Let's change that real quick. It starting from rest, and it rolls without slipping down a ramp of height h. And we want to determine the speed of the cylinder at the bottom of the ramp in terms of h and fundamental constants. So here's our picture. Again, we've got the cylinder with initial speed of 0 at a height h, and a cylinder with a final speed greater than 0 at our reference height. We'll again start with an LOL diagram. But with this LOL diagram, it is possible for the object to have both a translational linear kinetic energy and a rotational kinetic energy as well. Let's remind ourselves of some equations that could be useful. Translational kinetic energy is 1/2 mv squared. We switched to using a capital M because now this is a rigid body, an object with shape that consists of many particles whose total mass is now capital M. It doesn't matter a whole lot, but I wanted to tell you why I made that switch. Rotational kinetic energy, it's very similar, but instead of linear inertia of mass, we have rotational inertia I, and instead of linear speed v, we have an angular speed omega, but it's still 1/2 rotational inertia angular speed squared. And we also want to remember later on that your linear speed is equal to your angular speed times the radius of the object. That's going to come into play later on. So with that, let's make our LOL diagram. First step, identify our system. It's going to consist of the cylinder, the ramp, and the earth. And this ramp needs to be in the system because there is a static friction that is torquing the cylinder to give it some rotation. Initially, there is no kinetic energy, there's no rotational kinetic energy. It is at a height h above the ramp, 4 blocks tall, same as the box, and there's no spring. In the final scenario, there is some translational kinetic energy because it's moving, but also it is rotating, so there is some rotational kinetic energy. There's no gravitational potential energy. We're at the reference height. There's still no spring, and the friction that's present is static friction that's torquing the cylinder. There is no sliding kinetic friction, so there's still no increase in thermal energy. And with that, we can write an equation. I'm going to move myself up here. I'm going to cover up some of the words, but there's a lot of math that's going to come up on the bottom of the screen. So starting points, similarly, initial energy equals work, or initial energy plus the working that's done to transfer energy equals your final total energy. In this case, the initial energy is still just a gravitational potential energy. The working that's done is 0. And in the final scenario, we now have the total kinetic energy being the sum of the translational and rotational kinetic energy. Substitute in some formulas. mgh for your initial gravitational potential energy equals 1/2 mv squared for your translational kinetic energy plus 1/2 I omega squared for your rotational kinetic energy. So far, not that much more difficult than the previous example with the box. It's just adding in another term because it's rotating. Now the tricky algebra comes in. So bear with me. We first use our relationship between linear and angular speed to replace omega with v divided by r. We're making this choice because we eventually want to solve for the speed of the cylinder. That's our end goal. Moving on, distribute that square inside of those parentheses. Each term in here becomes squared. Next step, the rotational inertia given for this solid cylinder is 1/2 mass times radius squared. So we replace I with that formula. Next step, r squared here in the numerator multiplied by 1 over r squared here in the denominator just equals 1. And so we no longer have any r squared term in this third expression. Next step, 1/2 times 1/2 is 1/4, and because multiplication is associative, we can drop these parentheses. We end up with 1/4 mass times speed squared. Next step, 1/2 mv squared plus 1/4 mv squared. Oh, sorry, that's not what I'm doing here. Here we divided each term by m. Every term brought mass to the party here, so we can divide m out. And now I can look here and say 1/2 v squared plus 1/4 v squared altogether equals 1/2 plus 1/4 is 3/4. Multiply that coefficient over to the reciprocal of that coefficient. Multiply each term by the reciprocal of that coefficient so that we end up with 4/3 gh equals speed squared. And now the very last step, take the square root of both sides and you end up with the speed of the cylinder being the square root of 4/3 g times h. Whew. A lot of algebra there. Take a moment, pause the video, soak it all in. While you're writing this down, I recommend 2 columns, the first column with the math and then the column on the right with a quick justification for each step so you can make sure you understand where each step of math came from. So pause the video, write it down. And now that we've done that, I want to do a little bit of a comparison here and say the speed of the cylinder is 4/3 underneath that square root, and the speed of the box, if we go back to the box situation, was 2 gh. So 2 gh under the square root versus 4/3 gh under the square root. So this is consistent with our conceptual understanding that the speed of the cylinder will be less than the speed of the box. The other interesting thing, though, for the cylinder and the box is that for the box, the speed is independent of the box's mass. And for the cylinder, the speed is independent of both the mass and the radius of the cylinder. All that mattered was the shape because we had this 1/2 term here that didn't cancel. And so what that means is we didn't need the box and the cylinder to have the same mass in our conceptual example. No matter what, a box going down a frictionless surface of height h will be faster than a cylinder that rolls down a incline of height h without slipping, regardless of the size of the box or the cylinder, and regardless of their mass. All that matters is the shape and whether or not it's rolling. Thank you for learning with me here. I hope this helps. And if you have any questions, as always, please do reach out.